we interrupt the normal programming of boring astronomy for some boring news, some breaking news.
Boring astronomy.
The Euclid mission has delivered early science data. Welcome back to Boring Astronomy. I'm Alessandro, your astronomer next door. It was only last week when we had the early release observations from Euclid. So what does this mean? Last week we saw these beautiful images of the galaxy cluster Abell 2390, the star-forming region M78, the spiral galaxy NGC 6744, the galaxy cluster Abell 2764, and this beautiful Dorado group of galaxies. This goes together with data which were released late last year, including the Perseus cluster of galaxies, the spiral galaxy IC342, the beautifully irregular galaxy NGC 6822, the globular cluster NGC 6397, and a super classic, the Horsehead Nebula. But why is this interesting? Why, apart from the fact of being extraordinarily beautiful, why are these observations interesting? Why is the scientific community interested in these observations? This is the interest in the Euclid mission. This is the paper which was released last week together with the first data, and it describes the Euclid mission. Euclid is a space mission of the European Space Agency, and like all missions of space agencies, it has a vast amount of collaborators. Here you have something like 3.5 pages of co-authors of the presentation paper. It is rare to find an article with a table of contents. The paper is so dense that you actually need a table of contents to navigate through the paper. I will not go into too much details, but ask, and I may try to do it. Euclid was designed to respond to a major question, which is, what is the universe made of? We know that dark matter and dark energy, they have an impact on how the universe evolves. And honestly, this is not the first time someone has done it. This comes in a long, by now, tradition of projects which are studying the evolution of the universe. And here, just to show you a few of the important projects, possibly the super historical one, 2DF, SDSS, and now then the modern ones like DESI, and also JPASS, which is being observed as we speak, is one of those projects which aims at studying the evolution of the universe. So why is Euclid unique? The thing is, Euclid is in space. And the idea is it will scan the sky looking for the distribution in 3 dimensions of the galaxies. Euclid is going to cover this sky area, all this area which is marked by the blue lines, so neatly avoiding the galactic plane and another plane which is what I'm trying to signal here, which is the plane of the ecliptic, which is basically where all the planets lie. The reasons for this is because in there we have a lot of dust, and that dust is somewhat masking, is in front of the actual signal that the mission wants to detect, which are the galaxies, which are best observed here, 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 and in this small triangle here. On top of this is going to have 3 deep fields, which are going to be deeper, This one in the north, this one in the south, and the Fornax cluster. The idea is to use two instruments, one working in the visual, this is wavelength, and this is the optical range. Human eye roughly peaks around here, about 5,500 angstrom, and Euclid is going to observe mostly in the visible. There's one instrument dedicated to observations in visible and one instrument dedicated to near infrared. Basically, these are the near infrared bands, and these are the near infrared spectroscopy windows. These lines here, this is the transparency of the Earth atmosphere. So you can actually see how big is the advantage of going to space, because basically all the light in here and in here is actually absorbed by our atmosphere, whereas in space you don't have this problem. You may ask, well, we all know that there is already JWST in space, and it's also again in M2. So why it is so important to have this mission? Well, the thing is, these are two projects completely different. Euclid, to some extent, is a modest telescope. It's only slightly larger than 1 meter of primary mirror. But the important thing, the main feature, is its vast field of view. The full moon falls comfortably in the field of view of this instrument, whereas JWST has a primary mirror of 6 meters, which is, yes, almost 30 times bigger, but the field of view is tiny, is a fraction of the full moon. While Euclid has been designed to perform a wide field survey, JWST has been designed to observe specific small patches of sky, and any astronomer can request to observe these patches of sky once a year. The Euclid mission is supposed to last 6 years, and this is how they expect to proceed with the observations. They basically expect to start from the first year, starting from the northern part in their coordinate system, and then extend towards the equator. Possibly the most interesting part is the timescale that the Euclid Consortium has agreed with the European Space Agency. Whenever there are big missions like this one, the science team of the mission and the Space Agency agree on a timescale.
And nobody likes to work with space agencies because they are really, really tough with timelines and schedules and acronyms and standards, their own standards, whatever.
So this is what it was agreed. So after the launch, there would be a period of commissioning which was very, very tough, and then 6 months of early survey operation, and there would be a first data release here. This was agreed pre-launch. So all the work which has been done to comply with the deadline of last week was work against the clock, super tough, and they actually did a fantastic job. Let's go and look at that job. This is the paper which describes the early release observations. The paper is very, very technical. Perhaps the most interesting figure is this one. As I just commented, Euclid is going to observe the regions which are within these blue lines. And the objects which have been observed are the ones which are marked here. This one, blah. And you obviously notice that most of these objects are actually out of the main footprint of the mission. There was an internal call for interesting objects, and these are the objects which internally the collaboration has agreed to observe. They are a series of objects which have their own intrinsic scientific interest, and they have been used to check, analyze, and verify the performance of Euclid. The paper describes in quite some detail the capabilities of Euclid and the beauty of this telescope. One of the figures that any astronomer would be very eager to check is this one. This figure shows you the error on the photometry versus the magnitude, so the brightness of the objects that you're looking at. And these are the 4 photometric bands. So as is written down here is the I, Y, J, and H. And you can see how they follow this sort of exponential growth. And this is very much nominal and somewhat what people were expecting for Euclid. I may want to speak very, very briefly about one of the papers which came out last week, mostly because it's relatively close to my science, so I have some closer grasp, and it's this one where they were looking at free-floating newborn planets in Sigma Orion. This is the image that they were working with, and this is interesting not only because they did the job, and of course because the image is very, very pretty, but also because, as you can see here, you have a high reddening region and a low reddening region. So you are looking at a lot of interstellar material on one side and less interstellar material on the other side. And you can see the real power of having a telescope in space. You can see that this object, which has, this is possibly a planet or a substellar object.
The limit there is a little bit, hazy.
And this is in the visible, and then here these are the infrared bands. And you can see that in the near infrared bands, the PSF is broader. And what Euclid allows you to do is you can go and you can put these objects on a column magnitude diagram. You can see that the benchmark objects, the objects which were known, fall on this side of this track, and there are some other known objects which fall where they're supposed to fall, and they've already been able to discover a bunch of new objects. Then you make a color diagram and you can confirm some of your objects. This is only the beginning. This was a very first data reduction, to some extent, without offending anyone, was almost a quick and dirty approach. This is not the final data. I'm looking forward to have the actual feeds data to be downloadable, and so that I can actually touch the data myself. But what Euclid promises is to be a massive revolution in near-infrared astronomy for the near future. So stay tuned, get excited, and as soon as these data are going to come out, I'm going to let you know. I'm going to put in the description of the video all the papers that came out last week about this data release, and I'm looking forward to talk to you again when we resume normal operations. Talk to you soon. Ciao.